Starting off where we last ended last class, we talked about probability properties a little bit and what they are. So probability properties, probabilities can only occur or only have values of 0 or all the way up to 1, and there can't be a negative chance. You can't have a negative 25% chance of winning or more than 100% chance of something occurring. And so like examples of where you would be probability equaling 0. I discussed something about my chances getting into Harvard. I'm pretty sure that is pretty close to 0, while the 100% chance of something happening is me having fun recording these lectures and giving them to you guys. Pretty neat what we're doing here. And so they can be expressed as fractions, decimals, or percents. So the probability of some event A can equal 1/2 as a fraction, or the proportion 0.50, or the percentage 50%. And an event has a probability of 0 only if it can never happen. So going back to my Harvard admissions, that's the probability 0. But again, having fun recording these lectures and bringing this to you guys is 100%. So it's certain to happen. Always happens. And so probability of the sample space equals 1 because that's a set of all possible outcomes. And then there's a 100% chance that you'll get a heads or a tails when flipping a coin. And using the complement rule, probability of A superscript C, that's just the complement of A, equals 1 minus the probability of the event A occurring. That's also known as the complement rule. And the complement of A means that A does not occur, so we could write that as probability of A not occurring equals 1 minus the probability of A occurring. And for example, if A is the event of rolling a 5 on a 6-sided die, then complement of A is the event of not rolling a 5. So our set A only has 5, while our complement of A set has 1, 2, 3, 4, and 6. The probability of A equals 1/6 because we only have one element of the set, and the probability of the complement of A is just 5/6, or also known as 1 minus 1/6. Another example, consider a system of 5 identical components connected in series. Denote a component that fails by F and one that does not fail by S for successes. So so the probability of all these components firing off and not failing or succeeding is 0.59. So let A be the event that the system fails, which means that at least one of these components fails and the whole system shuts down. So probability of A is just simply for A to occur, one of these individual components must fail, and that is just 1 minus this 0.59, and that equals 0.41. And outcomes in A include success, success, fail, success, success, which is 1, 2, 4, and 5. Those components work, but 3 does not. And the first 2 components failed, but the last 3 work, and so on. And there are 31 different outcomes in A, if you would write it out as a sample set. However, the complement of A, the event that the system works, consists of the single outcome of all 5 components firing and working, and we know that's the complement of A. That equals 0.59, and to show the work, probability of A equals 1 minus 0.59. And that's just 41% of the time that system of components will fail. Now we're going to go to this slide real quickly, probability properties. If A and B are mutually exclusive, then the probability shown here, there's no overlap. the probability of A or B equals the addition of the event probability of A plus probability B, and that's known as the addition rule. And the intersection, or also known as probability of A and B, and that equals 0. As you can see down here, there's no overlap. So now we're going to go back to this slide. A is the event of rolling a 1 or a 2 on a 6-sided die. B is the event rolling a 3, 4, or 5. So how we would write this in events would be A equals 1, 2, and B would equal the set 3, 4, and 5. So we have 2 elements in A and 3 elements in B. There's no overlap because 1, 2 is separate from 3, 4, and 5. So to get probability A or B, A equals 2/6, B equals 3/6, and it's just this addition, 2 plus 3, 5/6. Another example, in the 2012 Olympic Games, a total of 10,735 athletes participated. Of these, 530 represented the United States, 277 represented Canada, and 102 represented Mexico. What is the probability that an Olympic athlete chosen at random represents the US or Canada? So for this event, they are assuming that these events of being an American and Canadian are mutually exclusive. So to the solution to this, these events are mutually exclusive. You can't compete for both the US and Canada. So we have 530 out of 10,735 for the United States. You have 277 representing Canada out of the 10,735. So these are the probabilities of them. You add them together, that's the fraction form, and then if you convert it to proportion form, about 7.5% of the total athletes were competing for the United States or Canada, and that's pretty neat. Another example is, from your wallet, all the possible bills that you can have in your wallet are the $1, $2, $5, $10, $20, $50, and $100 bill. And let's just say your wallet has 2 different files. It separates 2 things. So in the front one, you have a $1 bill and a $5 bill, and then behind that you have a 5, a 10, a 20, a 50, and a 100. So if you would pull a bill from your wallet without looking at it, is our example. Why is probability of A or B not equal to probability of A plus probability of B? Well, we can see by this diagram and by these sets over here that $5 bill was both in our front and in our back file, and clearly shown here on the Venn diagram. So that's why they're not mutually exclusive, and that's why the probability of A or B does not equal the addition of those 2 events, or those 2 probabilities. And I just said this here, A and B are not mutually exclusive, and the intersection is double counted. Another probability property is the general addition rule, which we could use in the last example. So probability of A or B equals probability of A plus probability of B minus the probability of A and B, so the intersection of the events A and B. And we can see that by a Venn diagram here. That's the A and B. This is all probability of A. This is all probability of B. And since the intersection is added in twice, because we would add all of this, we have probability of A and all of probability of B, we want to subtract out this part that's being double covered. and that's what leads to the general addition rule. Going back to this, if we wanted to figure out what the probability of A or B is, so probability of A is pulling a 1 or a 5 out, and the probability of B is 5, 10, 20, 50, 100. Using the general addition formula, we have 2/7 because there's only 7 total different outcomes that you could have, 2 from your set. And then if we would pull out 5, we have 5 in our set B out of the total 7 different outcomes. 2/7 plus 5/7, but we have a 5 in both sets, right here and right here. We want to subtract out that one outcome, so therefore it equals 6 out of 7. Another example, a survey of college students asked the questions, are you currently in a relationship and are you involved in intercollegiate or club sports? The survey found that 33% were currently in a relationship and 25% were involved in sports. 11% responded yes to both. What is the probability that a randomly selected student is in a relationship or is involved in sports? So we can dissect this by the events R being in a relationship, and we have 33% up there, and S is the students involved in sports. While using the general addition formula, probability of R, 33% up here, probability of S, 25%, but remember, we have to subtract out the intersection of both of those events, and that's 11%, so we would get 0.33 plus 0.25 minus 0.11, and that equals 0.47. So the conclusion is that there is a 47% chance that a randomly selected student is in a relationship or is involved in sports. Another example. A lot of these are pretty important. So recent research suggests that 73% of Americans still have a home phone, 83% have a cell phone, and 58% of people have both. What is the probability that an American has a home phone or a cell phone? B, neither a home phone nor a cell phone. And C, a cell phone but no home phone. This is just another slide. So for A, if we wanted to find out the probability of a home phone or a cell phone, written like this, we would have the probability of 73%, because 73% of Americans have a home phone, plus the probability that 83% have a cell phone. So we have those two, but using the general addition formula, we have to subtract out that percentage that has both, which is 58%, and 98% of Americans have some access to a home phone or a cell phone. And then you could look at this from the Venn diagram, which is, you would have to do a little bit more computation, but you can see clearly 15% just have a home phone, 25% just have a cell phone. So there's that plus that, but then you add the intersection, and that's 58%, and that equals up to 98%. But using, we want to find out that the probability of an American having neither, we could have, which is just using the complement rule, 1 minus the probability of home or cell phone from earlier, which is 98%, so 1 minus 0.98, 2% of Americans don't have a home phone or a cell phone, and you can look at this using the Venn diagram. So none of these events occurring, well, that just equals 0.02 from right there. And the probability of a cell but no home phone, which is the probability of just the cell phone minus the home and cell phone. So we just need to subtract out that intersection because we're only concerned with only cell phones, and that's 0.83 from up here, minus the 0.58, which is the intersection of both, and you just get 25%. Or you could look at the Venn diagram as you do it, and you can see that it's just 25%. So another example, suppose the probability that a U.S. resident has traveled to Canada is 0.18 and to Mexico is 0.09, but to both countries it's 0.04. What's the probability that a randomly chosen American has traveled to Canada but not Mexico, traveled to either Canada or Mexico, or not traveled to either country? So for problem A, we can look, probability of Canada and not Mexico is a probability of Canada. If this slide isn't that clear, I can work that out in lecture sometime. But we know that 18% have been to Canada, and we're not concerned with Mexico at all. So we need to subtract out that intersection of both countries, which is 0.04, and you just get 14% of Americans have only been to Canada. And so the probability of either Canada or Mexico, well, that's just 0.18 from Canada up above, plus 0.09 from Mexico, minus the intersection of them being to both countries, because that's we need to subtract that out because it's already accounted for in these two probabilities. And that just equals 23%, and you can look at the Venn diagram to see how it's calculated. And the last question we were asked was neither Canada or nor Mexico, and that's just the probability of 1 minus the probability of something we got earlier, and that was the 1 minus the probability of either going to Canada or Mexico, and that's 1 minus the 0.23, and we just get 0.77. Another example, we surveyed students of a classroom which transportation they take to a class, divided by male and female, and then the different transportation methods, which are car, bike, walking, and bus. And the first we have is find the probability that a randomly selected student will take the bus, and then so we can see probability of taking the bus, 55 out of the total number of students is 278, and 55 out of 278. The next is be a male and take a bike, so we would look up here, male and take a bike, and you can see that 14 is circled out of the total number of students, 278. And the next example we want to find is being a female or walking to class. So we have the total number of females, 154 over 278, plus the probability of those walking, 37 over 278, minus the intersection of those both using the general addition rule. And there's the 3 circles that I pointed out. So that's how we write probability of female or walking, and those are the numbers circled above, and that's what you get, 166 out of 278.